Hi, this is a video for section 2, day 1, and if you turn to the section 2 notes, we're going to modify the problem set that you're going to work on. So today in class, what we did is we're going to cross out 3 and 5 and 7 and 6, and we're just going to do 1, 2, 4, and 8. And we're actually going to do 4 as an example here in this video, and then you can work 1, 2, and 8 on your own. So you can stop the video now and or pause it and go to this portion in your notes and cross these questions out, but leave the workspace available for working other problems on that page. Okay, I'm assuming you crossed out those examples and you still have your notes in front of you. And so the next thing we're going to talk about is going back to section 6.1. I want to modify this procedure a little bit as I was making observations as you were problem solving in your groups the last couple of days. Remember, this used to be a 3-step for solving, and it was separate, integrate, and evaluate. And I felt like there were some universal omissions in your problem solving I was just seeing in every group. So I want to tweak this a little bit. So if you go back into 6.1, and so go ahead and pause the video and find the steps for solving in section 6.1. Okay, I'm assuming you're on that page now. So we're going to keep this first step the same. We're going to separate you. You were really good in your groups about being able to do that. But then step 2, we're going to call it what it really is, and that is anti-differentiate. And so I was calling this integrate, and what was happening in your group is you were forgetting to put the plus C on the end. And that's really important, especially for step 3 to make sense. So let's change this to anti-differentiate. Still rhymes with separate, so we're good there in terms of being able to remember it easily. So anti-differentiate, that gets you your general solution, and that's a solution with plus C on the end. And then step 3, evaluate to find C. We're not changing that step. That's the same step as before. That's where you plug in the initial condition, the initial values, to find your value for C. And then I added this 4th step because what I noticed in your group was that you were really good at finding that value for C. Like for instance, the velocity and the acceleration, velocity, and position example you were working on yesterday in your notes. You were really good at finding those constants. I think they were like -1 and +2 or something like that. And you're really good at finding the constants, but what just about every group wasn't doing was writing the particular solution. So that's where the step 4 comes into play. So we're going to add a step 4 here, and we're going to call that rewrite. So in other words, you're going to rewrite your general solution, but instead of the plus C on the end, you're going to put that number that you got for C, that constant of integration, and that's our particular solution. That's our specific function that goes through that specific point. So go ahead and pause this video and get these modifications down to your notes in 6.1. And as you do that, we'll go back to this. Sometime next week we'll go back to solving differential equations. But for today, we're just going to do some more integration. Okay, I'm assuming you're back now and you've got these notes complete in section 6.1. So we're going to go back to section 6.2 now and start the notes for this section. So section 6.2 is called integration by substitution. And the essential question is, how is substitution used to make integration easier? So we know, I kind of got a little goofy here and gave you the Webster definition of substitution, but it's this action of replacing someone or something with another person or thing. So the idea is, you take something out and you replace it with something else. So we're going to discuss the substitution procedure, and then we're going to have you apply the procedure to a couple of problems. So this is just a discussion. It's not in your notes, but we're going to kind of look at today's topic in this sense. We're going to take a problem here, and we're going to turn what we are going to see in that problem into what we already know how to do. So in other words, here's a typical problem that we're going to be asking you to do today. But wouldn't it be nice if it just looked like this? This would just be a straight power rule. Or for instance, we're going to have you do an antiderivative that looks like this today. But wouldn't it be nice if it was just this? This is an x to the half power. Or we're going to have you do something like this today. Do the antiderivative of cosine of 7x plus 5. But wouldn't it be nice if it was just cosine x? In fact, we're going to even have you do things like this today. We're going to do this example in the video. And that looks really complicated. And so when we're looking at this, wouldn't it be nice to just have something like x to the 4th, just this power be the thing that we're worried about instead of all this trig. And then lastly, we're going to, by the end of this section, you'll be able to do an antiderivative that looks like this, which looks super complicated. But wouldn't it be nice if it just looked like this? This is an x to the negative half power, so it's still just a simple power rule. And the cool thing is through the substitution process, we can actually accomplish transforming all of these into what you see here. And we call that a U sub. And the only reason we call it a U sub is because what we do is we take out the variable x and we replace it with a substitute, and we call that substitute U. So we literally change all of this into things that look like this. And then it makes it much easier to integrate. This is a power rule, this is a power rule, that's a trig rule, another power rule, another power rule. So, so we're going to look at the process now that's going to be able to enable us to transform something that looks complicated to something that looks a little less so. And so, this is in your notes, and there's a lot of things going on here, but I'm just going to kind of paraphrase what's going on. So basically what we're looking at is in fact, I'm going to go back a screen. If you notice, all of these expressions, all of these integrands, they have a function inside a function. So they have a 3x plus 2 inside something to the 5th power, or they have a 4x minus 1 inside a radical, or they have a 7x plus 5 inside a cosine, or they have a sine function inside something to the 4th power. Or they have a 1 plus x squared inside a radical. So as you can see, we have functions inside of functions, and we've dealt with that before when we were differentiating. We would call these nested functions or composite functions. And so this U sub is literally the reversal of that chain rule that we used when we were dealing with composite functions. And so that's what this notation is saying here. Here's our composite function. Now, so we're looking for this pattern of finding a function and finding its derivative expressed right in the integrand. So if I go back to that previous page, we can start to see the indications of that. Like for instance, here's the sine x and here's its derivative cosine. Or here's 1 plus x squared, and if we differentiate 1 plus x squared, we get 2x. These things will explain a little bit too. We don't have a derivative here, but we still have an easy ability to substitute out what is inside the brackets or what is inside the radical. So this is, like I said, quite literally is the reversal of the chain rule. So we've got these steps here, and these steps are really kind of ironclad. If you follow them, you'll be able to do substitution on just about any integral. So let's just kind of look at these. We've got 7 steps here. At first, you got to figure out what to call U, and that is looking for that function, and then we're going to differentiate it, so we're going to get that derivative. So if we look at this problem here, it's example 4 in your notes. So it should be at the bottom of the first page of your notes for this section. And so this is going to really increase the number of functions that we can find antiderivatives for. And substitution is going to allow us to get back to a simple form. And so if we look at this, we see that right here we have a nested function. So we're going to call the inside, just like we would do with the chain rule, we're going to call this inside function U. So we're going to start out by saying take that inside function. Oh, and before we go too far, actually, I've changed this problem a little bit. I want this to be a definite integral. So put on the lower and the upper limits in your notes. And remember, in your notes, we're not going to do example 3, so you have all of that workspace at the bottom of your page to do this example. So we're going to take the inside function here and call it u. So step 1 is set the expression equal to u. You don't have to write that, but I would like you to identify this as step 1. So step 1 is, say, u equals sine x. Okay, then step 2 is to differentiate. Now again, you don't have to write these words, but I would like you to identify this as step 2. So if we differentiate this, du dx equals cosine x. And then step 3 is solve for dx. So remember, solving for dx here, we got to think of this cosine as cosine x over 1, and then we can cross multiply. So we get du times 1 equals cosine x dx. And then, so we get that. And then if we divide by cosine x, because we want to solve for dx, we get something that looks like this. Du over cosine x equals dx. So we have a dx equal to this expression. So if we look at what we started with and what we ended with, we just swapped the denominator and what was that, and the derivative. So we just swapped those two things. That's kind of what the cross multiply and divide does in this sense. Okay, so step 4, we're going to substitute the u and the dx into the integral. So here's the integral. So if this is u, then we're going to take this out and put a u here. And if this is dx, then we're going to take this out and put this in there. So it's going to look like this. We're going to have the integral. Now notice I've dropped the upper and lower limits. And that's because I'm starting to substitute expressions that involve u in there. And these limits, this lower limit and this upper limit, pertain to variable x. So when I start to put in variable u here, when I start to do my substitution, these limits are no longer valid. So what I'm doing right now is I'm doing anti-differentiation. And I'm not paying attention to the bounds right now. Okay, so I'm going to go ahead and put in u. So instead of sine to the 4th, it's u to the 4th. This stays right where it is. Remember, this was the derivative of that. And that's going to stay put. And you'll see why in just a second. And now I'm going to do my substitution on my differential dx. So I'm going to put du over cosine x. So here's my substitution step. And if you notice, it's a mixture of x's and u's. But if you look a little closer, you can see that we have some canceling that can occur here. And that will always happen. So step 5 is whenever we are left over with x terms or x expressions, those should end up canceling. If they don't end up canceling, then you've done something wrong here with the derivative. So we're going to go ahead and cancel those cosine x's, and if you notice, once they cancel, we're left solely with variable u. So we have this expression that is u to the 4th du. And so now we're going to anti-differentiate that. So this is, I mentioned it when we had the screen of all those functions up. Wouldn't it be nice if this was just x to the 4th? Or u to the 4th. So now we're going to anti-differentiate this. So we're going to bump up the power and divide by the new power. So it's going to look like this. Okay, so now that's the end of step 6. So step 7, we have to make a decision whether we do a 7a or a 7b. And a 7a is for when we have a definite integral, which we do. And a 7b is a lot shorter, but it's for when we just want the antiderivative. In other words, when we just want to put a plus c on the end. We're actually going to do both of these steps just to show you the different variations. So here's the antiderivative. I haven't put the plus c on here yet. I will when we do step 7b though. Okay, so we're going to do 7a and then we're going to come back to this step and do 7b just to show you how they both play out. Okay, so let's talk about 7a. Evaluate with new upper limit and lower limit. So if you remember, we had, and I wish I would have had it come up here, but we had u to the 5th over 5. And these are x limits. So we've got to get our new limits in terms of u. So if you remember our substitution, u equals cosine x. So when x is a half, when we're at our upper limit, x is a half, then u is sine, excuse me, not a half, pi over 2. U then is sine of pi over 2, because u was sine of x. So sine of pi over 2, remember that's the top of the unit circle. Sine is the y coordinate, so u is equal to 1. And then for the lower limit, when x is equal to 0, u is equal to the sine of 0, and 0 is the right-hand side of the unit circle, and that y coordinate is 0. So if you notice, our lower limit didn't change, it's still 0, but our upper limit changed. So with those new limits, we can now evaluate the antiderivative. So remember, here's our antiderivative, u to the 5th over 5, or 1/5 u to the 5th. And we're going to evaluate that at 1 and at 0. So we're going to plug in our upper bound, which is 1/5 times 1 to the 5th power. And then we'll subtract and plug in our lower bound, which is 0. So this whole thing is 0 over here on the right. So our derivative, our definite integral is then 1/5. 1/5 times 1 to the 5th power. So our definite integral is 1/5. Now let's do the other scenario. Let's do the 7b scenario. Let's pretend that there is no upper and no lower bound. And so our antiderivative is 1/5 u to the 5th plus c, because it's an antiderivative, so it has a constant of integration. This represents, remember, the family of functions. And then what we have to do for step 7b is we have to substitute in what our expression for u is, because we need to get our answer back in terms of the original variable, which is x. So remember, u equals sine x. Oops, and I guess I don't have that written. U equals sine x. So this whole answer then is 1/5 sine to the 5th power of x. And I apologize for not having that written there. And that would be kind of a 7b approach. So at this point, now that we've gone through example 4, we can take that off the list. So I'm going to have you go back and try examples 1 and 2 and 8. And Friday in class, everybody got through example 1 and they were into example 2. So if you can get at least that far, then you can start the day 1 homework. And then Monday, you can finish up your examples and then do your day 2 homework. So that kind of takes us to the end of what happened in class today. As you're working on this in your day 1 homework this weekend, if you have any questions, just email me, and I'll definitely get an answer back to you right away.